Alright friends, welcome back. In this video I'd like to go ahead and talk about section P.4, which is going to talk about pretty much the opposite of what we talked about in the P.3 video. We talked about more of how to expand polynomials whenever we're trying to add or subtract or multiply them. Here we're going to go in the reverse direction. Instead of expanding things out, we're going to be factoring polynomials, and I want to go ahead and review some of that. So to just be clear, whenever we say a polynomial is completely factored, this is what we mean, right? So a polynomial is completely factored when it is written as a product of factors with integer coefficients, okay? And I'll show you the process for doing that as we go through. So there's a couple different ways to factor. We can do a GCF, or removing a common factor. Typically you guys will hear me say in class this GCF. That just stands for greatest common factor. We want to look for a common factor, but the biggest one to pull out of each term. We have some special polynomial forms that we need to be on the lookout for, so difference of squares, difference of cubes, sum of cubes. Maybe we can take a trinomial and split it into two different binomials. And then there's also grouping. And specifically, this is what we use for four-term polynomials specifically. So if you are factoring polynomials and you notice that you have one with four terms that you need to factor, we'll typically do that by grouping. Okay, so let's talk about removing common factors first. This is really simple. This is something you guys talked about in probably both your Algebra 1 and Algebra 2 classes. But here we just need to go ahead and look at both terms that we have and see what they have in common so that we could factor that out. So here in this first example, it looks like we have a 6x cubed minus 4x. What I always typically like to do, this kind of helps me, you don't have to do this, but I always kind of like to write a line under each one, and then below I like to kind of write what they have in common, right? Kind of like I'm dividing it out. So what's the most that these guys have in common? Well, the first thing I'm looking at are the coefficients of 6 and 4. I know that both of these have a common factor of 2 that I can divide out of both, right? Now I'm switching gears and I'm talking about the x's. I'm looking for the most number of x's that you could factor out of both. And since the second term can only give up one x, then we'll just say that the first term will also have to give up one of its x's as well. And so what this is right here, what we've just written is the greatest common factor of these two terms in your polynomial. And so what we'll do to write this factored is we will write the greatest common factor first. That is just the monomial 2x, it turns out. And then in parentheses, we'll write what's left over after we factor that out. So after factoring a 2x out of a 6x cubed, we're going to be left with 3x squared minus simply a 2, because that's what we get when we take 4x and divide it by 2x. And that's going to be our factored result. It looks like we have two factors in this factorization here, and that's pretty good. Always really good to check to make sure that what you are left over with cannot be continued to simplify. And looks like I was trying to switch to my highlighter there, and it was my pen. So looking at your leftovers here, in general, a really good idea would be to take a look at that leftover part and see if there's anything more that you can do in addition to what you've already done. Here, I don't think that's the case, so we'll go ahead and just box that and move on to the next one, right? So we have a trinomial here, and again, we're looking for common terms first. So again, I always typically like to look at all three terms individually, and it looks like since my third term is just a constant of 8, what I'm going to do is look at the coefficients here and see if I can factor out anything that might look like something that all three of these have in common. Now, because we're all dealing with even numbers, one of the things that we might be able to factor out in each one of these is simply a 2. Okay? So let's go ahead and take a look at what that would look like here. But actually, instead of 2, let's take that back here real quick, because what we said before in the previous slide was what? We said that it's going to be completely factored if we have integer coefficients, right? My note-taking program is taking a bit. Yep, there we go. Integer coefficients is what we need. So if we were to factor out a 2 from that problem, we wouldn't accomplish that goal. Instead, what we would really like to do is get rid of this 1/2. So let's think about factoring out a 1/2 from each of these, okay? It might be a little bit weird to kind of think about it that way, but let's go ahead and take a look at what that would be, because our first term, when we write our leftovers, is just simply going to be x squared, and that's pretty good, okay? But what does 2x become? Well, if I'm factoring out a 1/2, what I want to be able to do is write something here to where if I distribute that 1/2 back in, like working backwards, I would get back a negative 2x. Well, here that would have to be negative 4x, okay? Again, think about yourself working backwards. If you were to distribute in that 1/2, 1/2 times negative 4x would be the negative 2x that we had here originally. So that checks out. And then finally, for that constant of 8, I believe that would have to be a plus 16 for the same reason that we just talked about there. Now, Again, this might be something that can continue to be factored. Here, I think we're just looking for factoring each expression here, and I believe later on in the video we're going to talk about how to factor trinomials here. So for right now, since we're just focusing on factoring out a common term, we'll just go ahead and call it there. Maybe later on we'll get to an example where we're going to be able to factor that a little bit more completely. Moving on here to this third example, even binomials can be a greatest common factor here as well. So if you look at the terms, and remember that terms are separated by plus or minus signs, it looks like the second term can give up a copy of this binomial, 2x plus 1, and of course the first term can give up at least one copy as well because it has two copies of that. And so if we go ahead and factor that out as a GCF, this binomial 2x plus 1, then we are going to be left with, on the inside, parentheses, a second set of 2x plus 1, because that would be our 2x plus 1 squared in our first term, and then our minus sign, and then we factored out a 5 from that. Okay? Now, here's one of the things that we can just do really simply. This leftover bit can be simplified, okay? So we're not asking the question, can it be factored further, because the answer to that question is no, it can't. But we can continue to simplify this by writing our GCF out front, the 2x plus 1 we pulled out, and then times the leftover bit. So that would be, combining the positive 1 minus 5, that would simply be a minus 4 here. So 2x minus 4, okay? So now again, take a look at what you've got there and ask yourself what we ended up with. Can that continue to be factored? And I definitely think that it can, because we have a coefficient of 2 and a constant of 4. You could pull out a 2 from that, right? So we can go ahead and write that as, switch back to my pen, the GCF, 2x plus 1 that we pulled out earlier, and then we could write this as 2 times x minus 2. And then if we were to write that a little bit more succinctly, we could write that factor of 2 out front, and then x minus 2 to follow up times 2x plus 1. So using associative or commutative properties of multiplication there, we can go ahead and rearrange our factors in that way. So writing it completely factored, and again, you know, we could have done that second example more completely factored here, so let's just go ahead and accomplish that. So that would be 1/2 times, that's a trinomial, so we're going to unfoil this, so x and x, and we're looking for two numbers that are going to multiply to give us 16 and add up to be -4. So let's see if we could think of any. So let's see, factors of 16, we could have 4 and 4, or we could have 2 and 8. I don't believe any of those factors would actually get us to a point where we will be able to add them up to get a -4 here. So I think we were right in our very beginning assumption that this was the most that we could do on that one. It's always good to check, though, so I'm glad we checked on that. A couple of shortcuts here, so a couple of special factoring forms to just be on the lookout. This is called difference of two squares. So if you have something squared minus something else squared, that's the form that we need to be on the lookout for. And if you notice that you have that form, you can go ahead and immediately factor into this right here, okay? And so in our first example, the question is, can we think about this as something squared minus something else squared? And I think, of course, we can, right? Especially that 4. That can be written as 2 squared, and that 9x squared, that can be 3x squared, okay? Well, we notice that that is the difference of two squares, so what we will do is go ahead and write this out as the sum times the difference of our two terms here. And it is going to have to be the terms that we said we'd have to square to get what we originally had. So this is going to be 3x and 2, and that will be our final result there. Okay, so it's noticing that you have the form, and then after that, applying the form. Okay, same thing here. Can we rephrase this as the difference of two squares? I think we definitely can. The two things that we're squaring here are 7 and then 6y, the monomial. Okay, so very straightforward there. Again, there goes the sum, there goes the minus. It says as soon as you notice that you have a difference of squares that you can apply the formula, and we are cooking with fire here. Okay, that'll be our final result there. And if you don't believe me that these truly are the factorizations, you can FOIL these out and see that you just get the original back. Okay. The next one here, is this a difference of two squares? Well, I think pretty obviously that first one is, because it has literally the parentheses squared. So that would just be the binomial x plus 5 squared. And we can also write that 25 as something squared. That is just simply the number 5 squared. So this is the difference of two squares. So here goes the sum, and here goes the difference. Okay. And the first term that we said was simply the binomial x plus 5, and the other term was simply just 5 in place of there. Now, if you look at the two terms individually now, we have some things that we can continue to simplify. So, namely these constants. So that first term, that's x plus 5 plus 5. We could write that as x plus 10. And next, we can go ahead and see that that is just going to be x plus 5 minus 5. That's just going to give us x, okay? So we could either write it like that, or we could write the monomial so that it comes first. That's a little bit more conventionally accepted there. So I'm going to go ahead and write my final result in that way. There we are. Okay. So moving right along, some more special factoring formulas. This is what happens whenever you have a trinomial and you notice that it fits the form of one of your expanding formulas from the past video, right? So this is where you could factor into a perfect square. So in this trinomial, you definitely notice that the middle number is 6 and the last number is 9. Thinking in terms of, what are two numbers that might have to multiply to make 9 and add to make 6? Pretty straightforward here. I think those numbers are just simply going to be 3 and 3. So we might notice that this is a perfect square trinomial in this way, an example of this first formula here. And so we'll just go ahead and apply the formula, right? So the sum of two things squared, I believe we're going to have x and then simply 3 is the binomial that we would have to square there, x plus 3. On this next one, a little bit harder to notice, but it's still something that is considered to be a perfect square trinomial, because if you notice, we can rewrite this guy as 6y squared, and then this very last term, that's just 81, we could write that as 9 squared. So this is going to be a perfect square trinomial if we check that middle part and we confirm that it is negative 2 times u times v, or in other words, negative 2 times 6y times 9, and I definitely think that that works out here. So because we notice that we fit the formula, we can go ahead and just apply the perfect square formula there, and then call this 6y minus 9 all squared. And notice that that's going to be our final result there factored. Okay, so it's a matter of checking against the formula and then being able to actually apply that formula to factor correctly. Okay, some last ones here, some special factoring forms. These are sum and difference of cubes. So if we can write what we've got as something cubed plus something else cubed, or something cubed minus something else cubed, then we're going to be able to apply this formula, and it's really easy that way, right? So I think we could definitely do that here for this first example. This is the sum of two cubes, namely the things that we're cubing are x and 2, and so we're just going to go ahead and simply straight up apply the formula here. So that is going to be binomial u plus v. Here playing the roles of u and v are simply going to be x and 2. And then we follow that up with a times a trinomial. So that's going to be u squared, or in other words, for us in this example, x squared. And then minus what we get whenever we take u times v. Well, playing the role of u is x, and playing the role of v is 2. If we were to multiply those together, we would get simply 2x. And then finally, for that v squared at the very end, that would just be plus 2 squared, or in other words, simply just 4. And that would be our final result for how that factors. It has always seemed so incredibly odd to me that something that's so short written on the page would factor into something that takes so long to write on the page. I always thought that was kind of funny. But here, in the next example, still again, we can rewrite this as something cubed, but this time minus something else cubed, because that's the operation that we see. What we would have to cube here in this case would be 3x and, of course, 1. So really quickly, applying the formula from up top, that would be the binomial 3x minus 1 times the trinomial. Now be careful here, because we are going to have to square what's playing the role of u, and for us playing the role of u is that 3x that's sitting there, whereas playing the role of v is just 1, right? So we were to have to square that in order to get our first term of our trinomial. So we're going to have to take 3x squared, and that's going to be a 9x squared when we write that out. We need to follow that up in the formula with whatever u times v is equal to. Well, playing the role of u is 3x, playing the role of v is 1, and so 3x times 1, that would just simply be 3x. So we're just going to pick up here with a plus 3x, and then finally we need to tack on or add on v squared. Playing the role of v is just 1, and 1 squared is just 1, and so there we have it right there. Okay, so there is the factorization of that difference of two cubes that we had. Factoring trinomials is probably one of the more, process-intensive parts of factoring, but in general, it says here, to factor a trinomial of this form, ax squared plus bx plus c, we're going to use this pattern, right? So what we want are factors of a that are going to act as coefficients on our x terms in our factorization, and then these constants in these binomials are going to be factors of c, okay? So another way I kind of like to think about it is, that if you were to FOIL this out, you would get back exactly what you started with right here in your original, okay? It says where the inner and output products add up to bx, okay? So this is something that you guys have seen before, so we're just going to go ahead and apply it to a couple of examples here and then move on, right? So we have this first trinomial, this x squared minus 7x plus 12. Now, the leading coefficient there is simply just a 1, and so really this is just a task of figuring out which two numbers are going to multiply to give us a positive 12, but those same two numbers are going to have to add up to give me a negative 7. And when you're thinking about these numbers, since we have to add up to something negative and multiply to something positive, that's kind of a dead giveaway here that both of the numbers are going to have to be negative, whatever we pick. Okay, so in order to do this, I would just scan through the list of all the different factors of 12 and then just mentally check which ones are going to add up to that negative 7. And I definitely think if you think about it here for a little bit of time, you're going to see that the two factors that we need are going to be negative 3 and negative 4. So for that reason, when I get to the multiplication, or the factorization, I should say, I'm going to write two binomials. The first term in here are just going to be x and x. Remember, these would be the terms we would multiply in f of our FOIL if we were to expand this out. But then to follow up here with, we're just going to go ahead and say minus 3 and minus 4, because those are the numbers that we decided would give it to us a second ago, right? So there's a factorization of that trinomial right there. In this next example, we want to go ahead and think about how the FOILing would work if we were to expand something out and get what we have written here as the final result, okay? So when we write out our two binomials, when we write out our two first terms, we're going to have to think about how to break up a 2x squared so that if we were to multiply them using f in our FOIL, we would end up with that, right? So I think thinking about it a little bit would result in maybe just saying that those two terms would be 2x times x. That would give us the f in FOIL and give us this first term, right? That very last term, now that's negative 15, okay? So what we need to think about here is the L in FOIL. We need to think about what we would have to put here so that if we were to do the very last step of FOIL method, which is to multiply last times last, we would end up with a negative 15. And luckily for us, negative 15 is a number that doesn't have too many factors. 3 and 5 are basically going to be the factors that we're going to want to take a look at here. But that kind of begs the question, you know, what goes in what space? Is it going to be the 3? Is it going to be the 5? Which is which? Well, in order to figure that question out, we need to go ahead and take a look at our middle term here. We know that whatever we put in these spaces, whenever we FOIL it out, it's going to have to be one of those things where they're going to have to add up to a positive 1. And so this is just kind of playing with it and guessing and checking, right? Let's just say for a moment that I put a 3 here and a 5 there, okay? If I were to mentally kind of think about FOILing this out, then the f in FOIL, of course, we already kind of set that up for success. That would give us the 2x squared that we had in the beginning. But then when I would do my, my outer, that would be 2x times 5. And that would give me a 10x, which I will just kind of keep track of over here. This is something that you could totally do mentally. And then when you do your inners, that's going to be 3x. Well, that's going to be a 3x there, and depending on the signs of these numbers, we're either going to add these two together or we're going to subtract them together. Either way, we're not going to end up with a positive 1x result there. So I don't think 3 and 5 should be the ones that go into these spaces. Okay, we got to think about when we do the FOIL method, what's going to end up with what we want to have, right? So maybe let's reverse those. Maybe let's put the 5 here and let's put the 3 there. Okay, if we were to do the O in FOIL, that's 2x times 3. That would give us 6x. And if we were to do the I in FOIL, that would be a 5 times x, which is 5x. Okay? So I think this could definitely get it to us if we could force this to be a minus, because 6x minus 5x would give us the 1x that we want to be left over with here. So we would just need to play with the signs over here so that that happens. Keep in mind when you do the L in FOIL, we want to end up with a negative 15. So in order to go ahead and leave us with a positive 6x, I think this would have to be positive here because that means the O in FOIL becomes 2x times positive 3. And then this guy can be our minus sign here for our negative. Okay, so that'll give us our minus 5x. So our final result here is just going to be 2x minus 5 times x plus 3, and that will be our final result. Okay? I'm going to go ahead and skip that next one. It would be just more of the same here. It would be just kind of guessing and checking like that, writing two binomials, and then thinking about all the different ways that you could break up a 6x squared. Now, what I kind of like to do in these problems here is do a little bit of a chart. So maybe say one way I could do it is 2x and 3x. Another way I could do it would be 6x times x. Those are all the different possibilities there. And then if you look at that last term, thinking about the L in FOIL, luckily for us, that's the prime number 5. So really, it's only going to be factors of 1 and 5 or 5 and 1. And so what we would have to do is just kind of basically play with what we would put in these different positions in our binomial to get this to check out, okay? So you know what, let's go ahead and actually do this one instead of skipping it. So let's maybe say for a second that we suspected that maybe we can break this up as 2x and 3x, right? Well, since the only factors of 5 are 1 and 5, then maybe let's just go ahead and play with it and say, will this work? Will putting a 1 there and a 5 there work? And again, this is just kind of guessing and checking. What I'm immediately doing now that I've written this is I'm thinking of my I in FOIL and my O in FOIL, okay? So thinking about that, the O in FOIL here would be 2x times 5, and the I in FOIL would be 1 times 3x, okay? So doing the O in FOIL would result in a 10x, doing the I in FOIL would result in a 3x, and keep in mind what we want these to add up to. We want these to add up to that plus 17 in the middle, so we must know that we need to kind of play with the positions of what we have written here, okay? So maybe instead of the 1 there and the 5 there, maybe let's reverse that order real quick. Maybe let's instead do the 5 here and the 1 there. Will that give it to us? Well, I don't think so, because when you do the O in FOIL, that's going to give you 2x. When you do the I in FOIL, well, actually, hold on, I take that back. That will give it to us. Yeah, because that will be 15x, and then that will give us the positive 17x that we have there in the middle. So by doing that more of like kind of guess and check method, we can arrive at the answer pretty simply. Now, there are set processes for being able to go ahead and factor these in general. Those will be ones that if you're interested in learning about those, then you can come see me. But I think this is the most efficient and the fastest way to go ahead and get to these factorizations. And so that would be the way that I would encourage you guys to go ahead and think about doing these problems. Okay? Factoring by grouping is what happens when we have 4 terms. It's something we kind of pointed out before, right? So really simply done. Let's go ahead and demonstrate how to do this. I have a 4-term polynomial here. It's called grouping because what we do is we group together the first 2 terms and we group together the second 2 terms and then use backwards distributive property to factor each one of these groups individually, okay? So if I'm looking at that first group, I've got 2 terms. I think the biggest thing that they can give up is an x squared in that group. So for that reason, I'm going to go ahead and convert that first group to saying the greatest common factor x squared times whatever would be left over after factoring that out. And here I believe that would simply be x minus 2. Okay? Now, when we factor by grouping, what we would really like to have is x minus 2 as our leftovers for the second group. And so what I'm going to do is I'm going to look at my second group and ask myself, what would I need to factor out so that I leave behind an x minus 2? And I think pretty straightforward here, that's going to be negative 3 here. So I'm going to factor out a negative 3 in that second group. And that's going to be, yeah, x minus 2 is my leftovers there. And now what I want you to notice is what we have left over here is whenever we factor out those GCFs in those 2 groups is that now these 2 groups have a common factor of these leftovers. And so what we will now do is go ahead and factor out those common leftovers, right? So that x minus 2 that both groups have in common, we're going to go ahead and say x minus 2 factored out, and that leaves behind x squared minus 3. So x squared minus 3, and that will be our final result there. Okay? So that's pretty good. The next one down, same thing, factoring by grouping. We're going to group together the first 2 terms, group together the second 2 terms. I think it's pretty straightforward in this first group that the common factor that it has in both of those terms is just simply going to be a 5. And for the second group, look at the signs that are in front of these variables, right? We have negative signs in both. So I think we could factor out a negative x squared from both of these. That's the biggest thing that both of them can give up. And keep in mind, we're looking for those leftovers to be the exact same whenever we do this. So let's check and see if it does. In that first group, we factored out a 5. That's going to be 1 plus x that we're left over with. And when we factor out that negative x squared in that second group, I definitely think that that is going to leave us with 1 plus x as our leftovers whenever we do that. So that's pretty good. And again, both of these groups will now have the common factor of this binomial, 1 plus x. So we're going to go ahead and factor that out as the common binomial there. So 1 plus x times the leftovers, 5 minus x squared. And that will be our result for that problem there. Okay? Factoring completely, right? So these might be some problems where we might do one step to factor, but then we would look at our leftovers and realize that we would have more to do, okay? So as an example of that, let's maybe take a look at this part A here. We have a binomial, x cubed minus 64x. The very first thing that you guys want to look for whenever you're factoring is a GCF. You always want to ask yourself if there's a GCF, and I think definitely here there is one because both of these terms can give up a single copy of x. So if we write that, factor that out, then what are we left over with? Well, that x cubed gave up one of its x's, so now it's x squared, and then we'll say minus 64 there, okay? Well, one of the things that kind of jumps out to me in these leftovers is that I was left over with 64, which I just know is one of those perfect square numbers. And so I might notice here that what I've got going on is the difference of two squares in my leftovers, and that's something that we have a special formula to be able to factor, okay? So there's the GCF of x out front. Keep in mind that doesn't go anywhere. We still want to have that out front, but we're just factoring the leftovers now, and we know that to factor a difference of squares, it's a sum times a difference, and we just need to figure out what we would square to get x squared. That would simply just be x. What would we square to get 64? That would simply be 8. So x and 8, x and 8, and that would be the complete factorization of that polynomial right there. Moving on into the next one, it looks like we have a trinomial here, but again, always ask yourself, is there a GCF that I could pull out first in all three of these terms? And I definitely think that there is one. As far as the coefficients are concerned, I definitely don't think we're going to be able to find anything that those coefficients are common because 2 is a prime number and 15 and 7 are both odd numbers. So let's move on to the variable terms. I think each one of these groups can give up at least a single copy of y. And so we'll go ahead and write that as our GCF times our leftovers here. So what's going to be left over? We're going to have 15 plus 7y minus 2y squared. Okay? So if we look at that polynomial, one of the things that might be handy for us to do if you want, you don't have to do this, but you can write that into standard form just so that your negative 2y squared term comes first, and then you can factor it as normal. Okay? But here what we would want to go ahead and do is think about how this would factor. And we could just go ahead and think about doing that chart method that we talked about in the previous slide, right? So if I think about factors of 15, I could have 15 and 1, I could have 1 and 15, I could have 3 and 5, or reverse the order of that, 5 and 3. These are all different possibilities for how to do the L in FOIL. For the F in FOIL, for the first terms, keep in mind I want to do a negative 2y squared. So that could either be negative 2y and y, or that could be positive 2y and negative y, and I think that would be all of the different combinations there. So if we are factoring this, keep in mind we're going to keep our GCF of y out front, and then maybe just go ahead and continue with your two binomials here, okay? So we want two terms that are going to multiply to make a negative 2y squared. So let's maybe just try out negative 2y and then positive y there, okay? So what we are now going to think about are these factors over here and which one we might be able to use to add up some terms to do our O and I to end up with a 7y in the middle, okay? So how can we think about doing that? Well, in order to get a 7y, it looks like I'm going to have to take whatever I put here and multiply times negative 2y when I do my I in FOIL, okay? So that's something that I'm thinking about whenever I'm doing this because I'm going to have to end up with a 7y, so that must mean that when I subtract something off from my outer, it's going to have to leave us with something relatively big, a 7, right? So that's kind of leading me to believe that maybe what we need to have happen here is that maybe I put my 5 here and maybe I put my 3 there, okay? Because if I do that, then my outer becomes 3y, and then my inner becomes a negative 10. Now, will that give it to us? Well, we're close. This will actually give us negative 7y. So we are close there, but maybe one of the things that we might need to do is flip-flop some terms here. So maybe let's instead try this. Maybe let's put the 5 there and the 3 there. Will that work? Well, here I think that's going to create a problem here yet again because the outer is going to turn into a 5y and the inner is going to turn into a negative 6y, and those won't add up to be 7y. So I think we were right in what we had it before, the 3 and the 5 in these destinations here. Maybe what we need to do is change the order of these. Maybe we need to say plus 3 there and minus 2y there. So the point is, you know, guys, you keep playing with it. I think, let's see, let's actually go ahead and just write down what the solution would be here. That is going to give us, or maybe actually let's try some different combinations here. Sorry. See, that's the thing with factoring, is that this guess and check method I think is pretty darn good, but we do have to kind of account for, you know, the different combinations that you can have of these terms. I definitely think that that's correct, what I currently have written there. So we'll go ahead and box that as our final result. Okay, and again, there are other more solid processes for being able to factor these trinomials. If you learned some from last year that you want to employ for this year, then you may feel free to go ahead and do that. Let me just check here how much more we have. See if my note-taking program will be nice to me here. Just a couple of more. Okay, I'm just trying to cut down on the simple video here. Instead of actually doing all these examples out, we'll just kind of talk about how they would be done, right? One of the things about this next one is that this is a difference of squares. So we would want to factor that into the sum times the difference in that one. Okay? Down here, this doesn't look like a difference of squares, but it actually is, right? Because we could write this as something squared minus something else squared. What do we square to get a x to the fourth? Well, that would have to be x squared. What could we square to get a 16y to the fourth? Well, that would be a 4y squared. So when you factor this is, of course, a difference of squares. So that's going to be a sum times a difference. And then you would want to factor that accordingly. So we would say x squared, 4y squared, x squared, 4y squared. Okay? Now, we can't just stop there, because what you may notice is that right here we have just written yet another difference of two squares. Okay? We can go ahead and rewrite this as something squared minus something else squared. And we can go ahead and say that that's just simply going to be x squared and 2y squared. And so we can continue to factor that. So x squared plus 4y squared times the sum times the difference. Okay? And so what are we going to end up having there? Well, we just said x and 2y, x and 2y, and that will be our quick and easy result, just like that. Example 4, again, always look for a GCF first. I definitely think that you can have a GCF of 5 here in this first one, so we'll factor that out first. So 5 times t cubed plus 8. And then if you look at t cubed plus 8, that is a difference of 2 cubes. Basically, that is going to be t cubed plus 2 cubed. And so that means we can go ahead and apply the sum of 2 cubes formula. There's our 5 GCF from out front, and then that would be t plus 2 times t squared minus 2t plus 4. Okay? And there would be the complete factorization of that one there. For the next one, again, always look for a GCF. Now, again, your GCF could be a binomial, and I definitely think that that's a possibility here. So let's just start at the very beginning. We have a 2 and a 6. We can factor out a 2 from both of those. Next, we have x squared here. We have x cubed there. Both of those can give up at least x squared. Okay? And then we've got these binomials, right? We've got 3 copies of 7x plus 3 in the first group, and then we've got 2 copies of 7x plus 3 in the second group. So both of them can give up at least 2 copies. So we'll go ahead and say that this is our GCF right here. Okay? So when we write out our factorization, we're going to say that our GCF was our 2x squared times the binomial 7x plus 3 squared. And then we'll go ahead and write what's left over there. Well, after you factor all of that out, what cancels? Well, the 2's cancel, the x squareds cancel, and 2 of those copies of 7x plus 3 are going to cancel with 2 of the copies from on top, just leaving us with a single copy. So we're going to go ahead and say that I have a single copy of 7x plus 3 left over in my first group. The operation is subtraction, so we'll go ahead and pick up with a subtraction there, and then we'll start canceling here in the second group. So 2 goes into 6 3 times, so we'll go ahead and write that, 3. And you notice that I opened up a set of parentheses there because we're trying to subtract off this whole quantity, so we're just going to be a little bit careful with our signs by doing this. Okay, 2 of the copies of x on bottom are going to cancel with 2 of the ones on top, just leaving us with a single copy, so we'll write that single copy over here. And then finally, both copies of 7x plus 3 are going to cancel with both copies that were on the top there. So we definitely just have that monomial 3x. Okay? Now, can we clean this up? I think we can. In the bigger set of parentheses there, we've got 7x minus 3x. That will turn into a 4x plus 3. And so here is the complete factorization when we are all said and done with this problem here. Okay? So we'll box this. There we go. Very last one, example 5, ACT prep question. Find all values of b, which where is there a b at? It looks like there is a b right here. for which the trinomial can be factored. Okay, so we have this trinomial here. For all values of b, we need to find, what makes this be able to factor, right? Well, one of the things that I'm noticing here is that in this trinomial, the leading coefficient is simply just 1. So if this does factor, thinking about foiling backwards, the first terms, when I multiply my first times my first as my f in FOIL, I need to make an x squared, so that is going to be the reason why I'm going to have x and x there. And then, as far as what's going to go in these other terms here, remember that these need to be some terms that are going to have to multiply to make 18, okay? These terms also have to add together to give us what b is equal to, okay? So, when we figure out what b is, we would have to go ahead and say, what are all the different ways that you could factor 18, and then that's going to mean certain values of b are going to kind of fall out of that. So let's go ahead and make that chart of factors of 18 like we did before. We can do 1 and 18, we can do 2 and 9, and we can do 3 and 6, and I believe that's going to be it, right? So these are all the different factors or pairs of factors of 18. You just multiply each one of these and you get an 18, right? Well, those would have to be the numbers that go here and here, which means that those numbers would have to go here and here as well. So basically, in each one of these groups of numbers, we would just have to add the results together, and those would be 3 different possibilities for what b could equal. So in that first case, let's maybe do 1 plus 18. In that second case, let's do 2 plus 9. And in that third case, let's do 3 plus 6. These are all candidates for what b could be equal to. Okay, so in that first case, it could be 19. In that second case, it could be 11. And in that third case, it could be 9. And these are the 3 values that b could equal if we want this to be factorable. Okay, so there we go. Pretty quick question there. All right, so there's your assignment for P.4. Sorry for the long video, just a lot to talk about. Let me know if you guys have any questions as always, and I will speak to you guys in the next one.